Welcome back to Applied Mathematics. In this video, I want to talk about numbers and measurement. Depending on your background in mathematics, it's very likely that most of the topics that we are going to be going through in this video are things that you're familiar with, that you've already studied before, and hopefully, in that case, this is a nice review. But if you haven't, this is a nice chance for me to make sure that everyone is on equal footing as we get started. Let me get my head out of the way and let's dive in. All right, first, quickly, when we talk about numbers in mathematics, we can be talking about any of a range of different concepts. The integers, the positive and negative whole numbers, are very often an important idea on their own. Right? Things like -4, 27, 5,200, 5,200. Those are all integers. Rational numbers are things that can be written as fractions, which includes things like -4 or 27, right? 4 over 1 is a fraction, 27 over 1 is a fraction, but also includes things like 2/3 and 9/7. The real numbers include all of the integers, things like 27, all of the fractions, things like 2/3, and then all of the other stuff that tends to show up, right? Things like pi, or the square root of 2, all these weird things that we would rather not deal with. An important idea that shows up when we start talking about the real numbers is the difference between an exact and an approximate value. I'll let you in on the secret history here. The idea of an exact value was not important to mathematicians until about the mid-1980s or early 1990s. That's when pocket calculators started to become prevalent, and being able to do complicated calculations of arithmetic by hand stopped being something that was necessary. So math teachers invented a way to make it necessary anyway. That's not to say that there's never a value in exact numbers. There certainly are places where it is a worthwhile thing to be able to do, but I like to call them numbers that only a mathematician could love. Because while certainly the square root of 2 tells me a value, if I tell you that I want you to cut a board to be the square root of 2 feet long, you're going to look at me like I'm crazy. Instead, for that, we're going to turn to a calculator. And in modern calculators, like the TI-36X Pro, not at all sponsored by Texas Instruments, just happens to be the calculator that I have laying around. All right. But in modern calculators like this, the display will give us exact values. If you tell it you want the square root of 2, it will tell you, oh, that's the square root of 2. And that's why they have a key. In this case, it's the one right here, which translates from exact to approximate values. And that will tell us, oh, you want the approximation of the square root of 2. That's 1.4142135562. No problem. Or is it a problem? Does putting all of that onto the page actually make sense in the way of measuring things? In the idea of measurement, there is the concepts of accuracy and precision. And the idea here is essentially, if you are doing measurement, the numbers are only as good as your measuring tools. Right? If you have the need of measuring long distances and you are measuring with a device that is only marked in feet with no subsectioning, well then your measurement of 3,768 feet is good to the nearest foot. If you then do calculations and say, oh yeah, that gave me a 1.414213562 foot difference between these two lengths, you only measured to the nearest foot. How are you getting all of these decimal digits? So we need to have a means of addressing that. And the means of addressing that are called the accuracy and precision rules. Right. Accuracy and precision are sometimes also referred to as the significant digits rules. When we talk about accuracy, we are asking how many I'll abbreviate that, I'll call it sig figs for significant figures or significant digits. All right, just a little bit less to write. And when we're asking about precision, we are asking where did we round? All right, so in this value, 1.4142135562, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. The least place, the place where we rounded, and that's another thing that's important. Your calculator has to round to display things. Right? There are more digits that would come after this number that just don't fit on the calculator's display screen. All right, but place values: tenths place, hundredths place, thousandths place, 10,000ths place, 100,000ths place, millionths place, 10 millionths, 100 millionths, trillionths. That is a tiny number. Did I skip from millionths to trillionths instead of billionths? I think I did. Right? Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths. Yes, this should be the billionth. Place. All right, so the accuracy of this value is 10 significant figures. The precision of this value is the nearest billionth. If it's in feet, it's the nearest billionth of a foot. I'll talk more in the next couple of lessons about how you can use the calculations that you are doing to address the way of rounding based on accuracy or based on precision. But very often you're going to see instructions that say, well, you not see instructions, you're going to develop your own instructions based on the calculations that you've done that might say, round to 4 significant digits. All right, starting with the 1 at the beginning, then the decimal point. The second significant digit is the 4. The third significant digit is the 1. And then the 4 over here is also a significant digit. So if I want to take that square root of 2 and round it to 4 significant digits, I would report it as 1.414. If instead I might want to round to the nearest hundredth, well, the hundredths place is that one right there. It is a 1, but it is that place value. So 1.41 would be the appropriate way of talking about that. All right. So again, I want to stress here, there's not a this is right or this is better. This is appropriate based on the situation at hand. All right. None of these, 1.414, 213,562, is not exactly the square root of 2. It's approximately the square root of 2. It is approximately to a relatively high precision, but it is not the exact value. 1.414 is also approximately the square root of 2. It's approximate to a lower precision, but it's still approximately that value. And so one of the things that we're going to pay attention to as we go through this course is understanding what kind of accuracy and precision we should have based on the measuring tools that we've used. Right? If you're measuring something using a ruler that's marked to the nearest eighth of an inch, then you have precision of the nearest eighth of an inch. If you are using a micrometer that will give you precision to the nearest thousandth of an inch, then you have precision to the nearest thousandth of an inch, which is much higher precision. Representing the tools that you use correctly is an important part of representing measurements correctly and understanding how the tolerance of the measurements you have plays into the rest of the system you're dealing with. All right. Something that I've kind of glossed over here. What makes a digit significant? Well, the question there tends to be, can we still represent the same number without it? So, for example, if I take the number 42.765, now you would never see anyone write a 0 at the beginning of a number. But technically speaking, that is a perfectly understandable value. But those zeros aren't really doing anything. So those zeros are not significant. Now, at the end of a number, again, that 0 isn't doing anything, but you do sometimes see that. We included a 0 at the end of a number after a decimal point intentionally in a place where we didn't need it. Why did we do that? Well, maybe we have a tool that will allow us to measure to the nearest tenth of a thousandth of an inch. And in that tenth of a thousandth of an inch place, there's a 0. Well, we want to make sure that we are specifying that we measured with that much precision. So we write the 0 there, even though it doesn't change the number. That means that this 0 is significant. Here we get to the kind of weird cases. Now I've gone from a decimal number to a whole number. There's a 0 in the middle of this number. A 0 in the middle of the number is always significant. There's also a couple of zeros here at the end of the number. By convention, zeros at the end of a whole number are not significant. This is where things get kind of tricky. Let me rewrite that number so you don't have to try to squint through my scribbling on top of it. 405,200. Let's say that this is a measurement in feet. 405,200 feet. The phrasing of that makes you think that if this is a measurement in feet, it's rounded to the nearest hundreds of feet. And maybe it is. That's kind of our default assumption. If we want to say that this number was not rounded to the nearest hundreds of feet, but it's actually precise to the nearest tenth or tens of feet, I can put a macron, a little bar, on top of a 0 to say, even though this 0 is at the end of the number, it's significant. I could do that in the tens place. I could do that in the ones place. Another option that I have is to go to scientific notation. All right, so the decimal point is usually here. 1, 2, 3, 4, 5 places is where I would have to move it. So if I called this 4.052 times 10 to the 5th, it's the same value in scientific notation. The nice thing about doing this is I now have a decimal point, so I've left the rules of how to deal with zeros in whole numbers, and I come back to the rules of how to deal with zeros in decimal numbers, and I could write that as 4.0520 times 10 to the 5th, or 4.05200 times 10 to the 5th, if I so desire. All right. All of these options give us different ways of representing how precise our measurement is, representing the tools we used for measurement and how they interact with the value. All right, with that in mind, let's go ahead and do a little bit of unit conversion. One of the nice things about unit conversion is that the conversion factors tend to be exact numbers, right? 1 foot is equal to exactly 12 inches. 1 mile is equal to exactly 5,280 feet. So when I want to do a conversion, maybe I have measured something 14,700 feet, and I want to write that in miles. Well, the way that I tend to write out conversion factors, I'll take that 14,700 feet, I'll put it over 1, and then I'm going to multiply it by a fraction. I'm going to arrange 1 mile in the numerator and 5,280 feet in the denominator. I know that 1 mile is equal to 5,280 feet, which means that if I take 1 mile and divide by 5,280 feet, I get 1. And multiplying by 1 doesn't change anything. But I have carefully arranged my multiplication so that the feet will cancel out. And I realized that I need to take 14,700, divide by 5,280, and that will give me the value in miles. In order to do that, I'm going to grab my calculator. When I put that into my calculator, well, sometimes it will give you that as a fraction. You'll again use the fraction to decimal key to get that as a decimal value, which is what we need in order to actually do anything with it. But now we still have the question of how do I round this calculated value? Again, because the unit conversions are exact values, the only thing I'm going to do is look at the number I started with. The measurement, 14,700 feet, had 3 significant figures. So when I go to my calculator, 2.78409, etc., I want 3 significant figures. 2.78. All right. In this course, you are very often going to see instructions that say round following the rules of significant figures, round following the rules of accuracy and precision, or round following the significant figures convention. They all mean the same thing, and the starting point right here, when you're doing a unit conversion, and your conversion factor is an exact value, and whenever you're working in the US customary system, your conversion factors are always going to be exact values. You look at the number of significant figures in your initial measurement, and you round your final result to have the same number of significant figures. All right, we've gone through a lot of ideas here. Hopefully they are all things that are familiar to you. Hopefully it's all coming back to you now that I have talked about this. But with that, I think I'm going to wrap up on this video, and I'll see you next time.